somebody who some of you may know, some of you might not, but this is Michael Demidenko, who is University of Michigan Ph.D. graduate who spent the past few years as a postdoc in Russ Poldrack's lab at Stanford. And today he's going to be discussing how to use a pipeline he created that allows you to analyze task-based fMRI data sets from OpenNeuro while emphasizing transparency and reproducibility, specifically using something called Fitlins. So Michael, please take it away. Thank you so much for agreeing to be here.
For sure. When I finished making this, putting it together about 2 months ago, I thought, how can I get feedback from the most diverse audience? And I thought the NII group is probably the most diverse audience that I've encountered today, as far as imaging folk go. So, thank you for joining on your summer. During your summer, I know things are quiet, and so and joining at a off time. Uh, can folks see my screen? Okay, cool. So I will be effectively going over this integration analytic pipeline that is intended to use OpenNeuro Task for my data. So we started this project about February, and we thought we'd have more barriers that we didn't encounter, which we did, but it went a lot quicker than we expected. And so it's at a stage where it works. You can run entire workflows, but also find it's important to get feedback so I can integrate it for the end users as well as folks that may want to use it differently. So currently it's set up that it works with OpenNeuro Task for my data, but I'm currently working on making it easier to work with any in-house task fMRI data. So I'll go over the workflow throughout. Feel free to ask questions, and then I will also go over a demonstration after my slides, which will take about 22 to 24 minutes. So to start off, I won't belabor the point. I'm sure many of you are familiar with OpenNeuro, the data archive, but it started in 2016 and rapidly grew and took off over the next few years. And since 2016, it has amassed over 1,400 data sets. That includes MEG, PET, EEG, IEG, I think NIRS data. There's task fMRI, resting state, etc., all on there. And then last I checked this morning, it's up to now 1,435 data sets. After the initiative started and they were trying to building out this archive where people can upload and share data in a bit structured manner, in the last few years, they've got funding and have been pushing an effort to generate derivatives. So compute time is very expensive for task fMRI data, as many of you know, and there's lots of task fMRI data sets on OpenNeuro. So they've been facilitating the pre-processing of these bold resting state and task fMRI in particular, given that is the point of easiest entry to facilitate this with MRI QC and fMRI prep. And Joe Wexler, since 2022, has been working on these, and we're currently at about over 200 fMRI prep derivatives and 300 MRI QC derivatives. And so when we were working on reviewing metadata and other topics with OpenNeuro, you quickly realize there are some unmet needs. Some of them are proposed in the grant that they currently have for OpenNeuro that's still ongoing to basically generate more flexible analyses of the data sets. But there's still a problem of the post-processing of time series as well. And so there's this problem, and I'm sure many of you are aware of it, since most of you here probably work with fMRI one way or another, or MRI in general. MRI has a lot of files when it comes to the raw and pre-processed data, particularly if you're using something like fMRI prep. So you can amass anywhere from 80 gigabytes with thousands of files for a single small data set, not even to mention the large data sets. Then when it comes to task fMRI, there is really an issue of complexity and heterogeneity. So each data set has its unique quirks, it has its unique models, and it has a lot of things and decision rules that need to be made to align the events, time series, and build your regression model. Unlike resting state, which is still challenging and difficult, but the decisions differ in what kind of filtering you're using, but you can ingest data in the same structured manner at the very least. There's just a lot more heterogeneity in task fMRI. And so there's been this gap where while OpenNeuro tells you use this link to download the data or use this way up data lab or AWS to download it, there are limited pipelines that facilitate the download, transformation, and analysis of OpenNeuro data and allow you to report it and share it in a reproducible manner. So if we consider that oftentimes you can go on OpenNeuro, there's some command line scripts and CLIs that you can use to download it to your machine. Then you have to figure out the behavioral brain and metadata stuff to then build your voxel-wise univariate models by fitting your task relevant regressors and nuisance regressors to those time series. So no such workflow exists. And so we've been trying to figure out how can we facilitate and fill this gap and this void that currently exists and do it in a way that is as reproducible and kind of expands on allowing to improve other facets of the fMRI as literature as well. And so that's where we came up with the solution of the Fitlins GLM framework. And I apologize, I have a 1.5-year-old awake and he's knocking on the door right now. So if you hear him, please ignore him. And so we developed this semi-automated workflow. And it's not completely automated because there is an important, it is important to have a user involved throughout, particularly in the early stage when a model and a spec file, which I'll discuss later, isn't established yet and provided. And it's intended to be at a very reproducible workflow. So you can just simply download the data, run it end to end, share it, and someone else could do the same thing. All they just need is learn a couple command lines. And so effectively, it starts by, obviously, we have the data on OpenNeuro. We have the derivatives on OpenNeuro. Now we can fetch the behavioral time series, but sometimes we may not want all of them. So for example, when you're building a task fMRI model, you might not really need the input bits data. So why do you download the massive nifty files and everything else that you may not want when you can filter them out? Likewise for fMRI prep, fMRI prep has like two formats where there's minimal and non-minimal derivatives for OpenNeuro. The minimal is more recent, where basically fMRI prep data are not fully derived. They give you enough so you can rerun it in maybe 15 and 20 minutes per subject. But nevertheless, they generate files that are pretty large if they're non-minimal, and they're oftentimes unnecessary. So you don't need aroma regressed nifty files, so you may want to exclude those. There's also free surface stuff you may not be interested in, or some kind of FS average surface-based outputs. And so the pipeline facilitates exclusion of file names and folder types to automatically not pull them down. So you save on space from, and I'll give an example later. And then when you get this data, obviously you go on OpenNeuro, you can click through and look at everything. You can open files when they land on your machine. But sometimes it's helpful just to get a quick summary of what about the data, what about the behavioral tests, what about the events files, so I can get more into like what I need to think about. Like, is there onset, duration, and trial type? If there's a trial type, what kind of values are in there? And what data types are these, or objects? Or are they numerical? Are they objects? Or are they some kind of other like integers, floats, etc.? So you can consider how you need to plan for the next steps. And then the next steps are effectively cleaning or preparing, transforming your data. So not sure how many of you work with OpenNeuro data, but the events files that are uploaded are sometimes a headache, or put lightly, a mess. So there's oftentimes a lot of cleaning that requires to be, that is needed when you're going through the workflow in order to get the data ready to then fit your models. And oftentimes this means going through papers, reading the method sections, because often the details aren't readily available. And so you need to do it in a quick and effective manner. So it's this consistent application to each like event file for subject, run, etc. And then once your data, say your bold files are trimmed, if there are calibration lines that need to be removed, and your event files are prepared, you have the regressors and you have the onset durations aligned with conditional values that you're interested in for your model, you build your model. And this is where we have the bid stats model, which is kind of the Fitlins wrapper that we focus on. And when you run this, we wanted to offer both a local option, so you can facilitate the run on your machine. But given the growing demand and use of high performance compute, we kind of create bash scripts as well, so you can submit Slurm jobs very easily by quickly modifying the file, so things go a lot quicker. So reducing compute time from, say, on your machine from days to, I think sometimes I've been able to run things in like 2 hours. And then finally, once everything runs, so depending on the group model, we want to also facilitate the reporting, an automated dynamic reporting styles that ingest all the program readable files. And because there's already structured ways of reporting, like the Kobados checklist that's created from OHBM, Tom Nichols and others, we want to facilitate the reporting so it's consistent, coherent, and it's not as variable as it currently is in literature, because it's often hard to sometimes understand what models people fit. And then finally, closing the loop, we wanted to make it open and reproducible and community informed, which that means is if I run a Fitlins model, or I have been doing thus far, I want to push these to Git repo that people, when they clone this repository, there's a data set listed that they want, they don't need to do anything. They just run each step and it'll give them the outputs that they want, and there's nothing else that they can do. Obviously, we're also trying to reduce compute time by pushing all of the task-based analysis outputs to S3 buckets so people can download them easily and not have to rerun anything. But that we're still working on that. So there's this whole workflow of a loop that you go through in the pipeline, and all of them are achieved in 5 bash commands, which I'll cover a little bit later. But the important part is, and the question is, like, what is the bid stats models, which is the back end of the model fitting approach, and why are we using it? So initially, when this first project idea came up, they were going to go strictly NiLearn packages, but we wanted to go back to Fitlins because it's been around. It's been around for a couple of years, and it seems like a practical use case. And so Fitlins basically uses bid stats models, which effectively uses machine readable files to run common univariate task fMRI analyses. And its original goal is to effectively reduce the manual effort by using a recipe that performs a sequence of steps that are nested. So it ingests your runs. So I guess a good example is, if anyone remembers a while back, maybe this is kind of aging myself, methods core at was around, it used a similar structure, like some template that runs things. So this kind of has a similar flavor, but different, where it has nested filtering, run, subject, and group models that are fit with transformations within each to perform different setups for each model. And its goal is to increase standardization. So the model specs are ordered in the way they are performed, and the derivatives are standardized in how they're reported and output for each run level, each subject, and data set. So you are familiar with what is performed in what sequence, because it's right there in the file, but you're also aware of what's going to be in the outputs and what they are, because it's named in the same thing for each node that's output. And also it's to increase transparency, because currently it's kind of hard to know what people run, but these recipes include information about the subjects, the runs that are listed, what transformations, so manipulations of the variables that are being input to the model, and then what models fit, so what your GLM is running, and your contrast specifications, particularly labels and weights. Oftentimes papers and ellipses, and so you're kind of guessing something like, I think I understand what they did, but sometimes it's different. And also, its bid stats model goal is to increase flexibility. So the default is to use NiLearn SPM framework, but it also allows the framework from AFNI, 3D REML Fit, and then they're trying to integrate FSL. So that means if you ever wanted to run a multiverse between these 3 different statistical models, you could effectively do it with just the same bid stats model spec file, which can run these 3 different things without creating code base that's different. And all 3 frameworks have different code bases, so it requires an expert in all 3 to understand. This allows the same person to be able to read one file and see what was done. And currently you can model your HRFs using this SPM, Clover, FIR models, currently resolving some issues identified in error, how the convolutions are occurring, but we're hoping that will be fixed for the FIR models in like the next month or two. And you have optional time and spatial derivatives for the shape. And then obviously BitStats model goal is to increase reproducibility because of the spec file can regenerate the same model. So if you have the same bid inputs events files and the fMRI prep derivatives, such as OpenNeuro, you can rerun it and get the same output. And an indirect goal, and kind of my interest, is also to improve reporting standards. So you have design matrices, you have contrast vectors, you have program readable files. So you can standardize reporting at each level. So for the run, subject, and the group. And so kind of like for fMRI prep, MRI-QC, you can use Cobodot's checklists to create boilerplates for what are being run. And I'll give an example later. And so kind of talked about model specs, and most people probably have not heard the term. If you have, you may be still curious. So what in the world is a model spec? So a model spec is just the specification file, which specifies the instructions for the engine that runs BitStat models. So I'll use an example because it's related to kind of what folks here are familiar with, and what Andy was indirectly involved in a while back, which is the NARPS data set, which people had 70 groups run the analyses and get different results. And this is kind of a perfect case where BitStats models can prevent some of these things. So a model spec for the data sets of NARPS on OpenNeuro, which is 1734, you basically start with the input, which inputs you can filter subject arrays, you can have run arrays and session arrays. So you tell the model, here's the subject and runs I want to start with and go with, because I excluded these subjects because I don't care. They're in the folders, but don't pay attention to them. Same with runs, and same with sessions. And then you have the which is the run level node. So the run level node basically prepares your events files to then fit the design matrix that you use in your GLM model. In short, what that means is you can demean regressors, you can convolve regressors, you can assign new duration values to regressors that live in a data set. So each step basically is a recipe for what to do to a variable that is in your events file for all subjects and what output it should get to use in a next step. And so if you just ignore these three steps, what the main and common theme that you use is basically you factor the trial type regressors, which basically means any nominal variable that exists in the column. We're going to create a 1, 0 for it as a new column, and it'll basically be appended with that label of trial type period something. So then you convolve those regressors. So we use SPM. You can use other models that can do the convolution, and you convolve it with the trial type column. So here you can use wildcards. So basically, if there's trial type .9 and you want all of them, you convolve all of them by just using a wildcard. And since we also have a gain that's demeaned, a loss that's demeaned, we also parametric modulators, we can also include those here. So this effectively just sets us up for the actual model that's going to be run voxel-wise. So you convolve your regressor, then you specify the model. So what are going to be the regressors that I'm going to be using for my events? And then also what regressors that are not convolved, my nuisance regressors that come from the confounds.tsv file from fMRI prep derivatives that I want included. And you can specify them here as well. And then you provide it the contrast list. So your labels, the names as they appear from the factor labels that result, and then the weights. So, are you just taking a value of condition versus some implicit baseline, or is it between conditions, some more complex model? So this gives you your run level model, which is effectively what we start with all cases. And then you have a subject level model. So if you have multiple runs, the model will dynamically add, the package will dynamically add and check and add this section, which will say, like, how are we averaging runs? You can run some kind of a weighted fixed effects model, this to say, I'm going to just take an average or some weighted average based on some variance of runs. And then you just finalize your data set. In this case, it's just a one sample t-test. We're just taking the mean, so effectively just an intercept. Hence, we only have a 1 in the model. But kind of given an example of where we're currently writing this up, but this repo here, Jupyter Notebook, has these specs more reviewed in detail. But you can run a number of models. And I use this data set because that's what we're using, because it has enough flavor to fit these. And use the root just in TSC to specify different group level models. So like I mentioned before, we based on these run level stuff, we can fit a 1 sample t-test. We can fit some kind of 1 sample t-test with a covariate. We can do a group comparison, just like some clinical groups. In this case, they had major depressive before, or never depressed groups. You can do the same thing by adding another covariate in there, or you can do some kind of interaction between the groups and covariates. So that way you have age for center with each group, and you can then effectively take the compare basically the slopes for them. And then you can go and do something like a NOVA and do an F test, and then make some kind of orthogonal contrast. So you don't need so you can control the family-wise error rates. So there's a number of group build models that you can fit that are more than just that 1 sample t-test. So to date, with this framework, so far, I've been able to run the end-to-end repo on 34 data sets across 55 tasks, and generated over 300 some contrasts with these group level reports. And these tasks span motor, decision-making, vision, auditory, control, risk-taking, social paradigms, and more. I don't have all of them because it's hard to memorize and list them here, but in the repo lists task names every single time it automatically runs. So I guess the interesting part is, how does this work? I gave you this loop. What does it actually do? So the first step, these 4 components are actually finished in a single step and 1 command line, all in one. So effectively, there's this batch command that you simply run. I demark them in 1, 2, 3, 4, 5. So it's order the structure. And I'll open the feedback to refactor it, clean it up, make it better, parse them out, etc. But you just specify the data set as it's listed, the data set ID as this OpenNeuro. And then it checks some things to first, does the thing exist there? Then what is the size of the BIDS input folders? What is the size of the fMRI prep? And checks if the fMRI prep is minimal or non-minimal derivatives. Because if it's minimal, you need to rerun this script, which I give you. It's a bash script to recreate the fMRI prep data based on the minimal inputs. And so it gives you these file counts, sizes, and if you want to be reducing the amount you're getting, if you want to run like say 20 studies, you might want to do, you leverage the file exclusion folder. So that way you downsize. But once you're ready, you just run it. It throws a bunch of things in the terminal, like what it's pulling down. So you can ignore those. But at the end, it gives you some information of the task, and other details about the subjects. But then it creates this automatic README file, which specifies your number of subjects, your trial types, and volumes for a given task. It populates MRQC reports via a link that renders the HTML when you're on an HTML rendering page, rather than trying to open up and not be able to read it locally. And so you have a lot of information here that you can start with and then kind of build out the next steps. It also generates automatically for each task a subject list file and a contrast, which is just a boilerplate that you populate with your labels and weights that are used in subsequent steps. So from here, you go into the transformation data stage. So again, just a script that you run per data set and task. And this, when the download script runs, it creates this data specific basic details JSON file, which is just easier to read. And it populates a number of things that you can update, like for the group level, what plotting coordinates to use. It just estimates the first count of bold volumes, not the range of that existing data sets. It has the dummy volumes. So if you have calibration volumes, how many do I need to cut off if I'm needing to update? The default is null. And there's this pre-processing events thing. So the default is, I think, null, but if it's true, it basically will tell you that you need to pre-process those events files. And the pre-processing of event files is a little bit, it's one of those involved parts where you basically, there's this modify events Python, which creates functions for each data set. And currently, I think there's, I don't know, maybe 20 as examples. And effectively, it says for this data set, if the task is so-and-so, we are trying to ingest the events files, and you follow like the same structure, just modify it for your case. Modify the information using this format, because currently there's kind of the data are messy or structured in an incorrect way, and I need to fix it the same way for everything. If you're not familiar with Python, I encourage you to not fear and just use Claude or GPT, and success will be near, because it is really good at these type of things if you give it clear instructions and an example, which already is there. And so effectively, when this modify events bold and events files runs, it basically pulls all the bold Nifty files, checks, confirms whether you specified dummy volumes. If you did, it trims those volumes and spits them out in a alternate derivatives folder that we then use. It also, in place, modifies these events files for each subject, each run for a given task. And it leverages Biz layout to kind of do this effectively and seamlessly. And then the third, and again, one of the involved pieces is the creating the specification file. So model specs are going to be the most error prone part, because you need to make sure the events are structured in a way information is there consistent with your contrast in your models. And try to put in a couple of checks in there so I can be like, hey, maybe you're missing something. Pay attention to this when you're building these to simplify it, but it's obviously not bulletproof. But effectively, like I mentioned before, the skeleton's already provided where it's for each task, a subject list and contrast that you can modify and tweak for your analysis. That then when you run this model specs, it ingests and populates. And so it uses a simple model spec to dynamically integrate this task information, and it incorporates the subjects, the runs, the sessions, and the contrasts. The important thing to always do, because it's boilerplate for the transformations and the group models, is once it ingests those things, you need to modify what kind of convolution you're doing, what transformations you need or you want. It has some defaults, but it's important to review those. What models and regressors are going to be in there. Again, it uses some defaults, good to double check. And then, of course, most people are probably not just interested in a one sample t-test. So you might want to model this group model, but I might try to see if I can modify it where I can dynamically create, say, two group ANOVAs, etc., rather than current format. But again, I think because it requires transformations that you need to do, those are just necessary. So it takes you probably 70% of the way to reduce like errors when you create these JSON files manually, but you still need the 20 to 30 to finalize them. And then I give the two options of submitting these batch jobs. So you can run it locally by just running in the scripts folder, this run Fitlins for each task, but it needs more memory. I've had it struggle when I didn't have more than 16 gigs of RAM. So it's compute heavy. So that's kind of slow and problematic. But also in the cluster jobs provided a batch script that facilitates this as well. This is the one I recommend because it's efficient and it's fast. Like you can, if you were running the NARPS data set locally, it would take you several days. But I think by running it on the cluster, I think it ran maybe in like 12 to 14 hours. And when this finished running, it generates a bunch of derivatives in your output folder, which gives you the effects, the p-values, the t-sets, z-sets, variance maps, the run level design matrices, r squared, so like how much variance in boxes your model's explaining, and some log likelihood maps. And it's consistent for each subject and each run as long as they don't fail and they're included. And so because not everyone's familiar with Slurm jobs and how, or these SBatch jobs and how they may differ, what you need to update. So Andy shared his like example of a Great Lakes submission. So oftentimes you kind of submit with an account and a partition, and that I use in mine. So in my case, we only need a partition to run these jobs, which obviously at you all would label it differently. But at Stanford, we don't need an account name, but at you do. So you specify account, you make these two updates, you're 70, 80% of the day there. The other 20% is just updating this where the log file where you're mailing. I don't want all of your emails. So if you use this, please update it so I don't get 1,000 emails if you run it 1,000 times. It's happened where people in our group use this and I just kept getting emails and like, I didn't run a Fitlins model. Why is it failing? I didn't do anything. And so I couldn't figure out what was happening. I had to email the help desk like, oh, is this person part of your group? I was like, yeah. And so just remember to update this. Maybe I should figure out how to strip my email so I don't get those. But in any case, once you update these two steps, the time component, you can adjust. Smaller days that take less time, large days more. The CPUs and memory per CPUs, this is like, I found this to be the most optimal for it to run as quick, both maximizing speed and efficiency. But yeah, otherwise, everything else runs below. It doesn't need to load any modules because it uses UV Program Manager for Python. And I specify some third things so it doesn't run away because I found getting emails that I was using more nodes than I was requesting. And then there's this summarizing script, which effectively you run it once your Fitlins model completes. You run it, and its goal is to improve like reporting, which is currently inefficient and variable. And so it uses the COGADOS recommendations, which is currently sparsely used in methods, based on method sections, but tried to dynamic create it. And the reason is I want to reduce all this variability and reduce the guesswork of what people run and why. So it gives you boilerplate name regressors, smoothing, convolution, number of interest, nuisance, and parametric regressors, whether run subject models are ran, the contrast and linear weights, which we're trying to use, currently incorporating some APIs which do pretty well to write a description of what those are. Like, what does this contrast measure? Like, give me like 3 to 4 words you folks are not guessing. The design matrices, regressor and contrast VIF to figure out how collinear these are in your model, and some quality control stuff, which I'll show you a bit later. And then the group activation maps across sessions and contrast if they exist. And so there's a number of strengths with that I won't go over because I think I'll just let questions for time and demonstration and questions. But basically this, before I go into demonstration, I think it's important to thank folks because I won't really come back to it. But Russ for being like, hey, you should do this. Let's see if you can do it. And Jeanette, who's worked with PyBids, Fitlins, and like answered some big issues. And obviously the development side, Chris Markowitz. Alejandro, who is at UT, who is part of PyBids and BitStats models, and Paul Jaff, who is now in industry, but he was really good at programming and initially started with the NiLearn stuff that we then refactored, but at least he got my brain, the wheels greased for how to think about the problem when I refactor it. So now I'll just go into the steps or demonstration, but before I do that, let's see how much time. Yeah, it would take only like about 5-10 minutes. So I'm open to questions if folks have them now. But if not, I can just also stop sharing and then go into the other screen. Yeah.
So just make sure that this assumes that everything has been already pre-processed through fMRI prep, for example.
Yeah, so the assumption is there are pre-processed derivatives for fMRI prep, and it pulls those for OpenNeuro. And so when we refactor and we do a version that's more compatible for in-house non-OpenNeuro data sets, it would also have to require fMRI prep to exist. Otherwise, it'll just fail because there's nothing to go off of. Yeah.
Got it. Okay, thanks. Anybody else? Okay.
Oops. All right. So I'll just go over a quick example of how this works. So to use it, to start off, you would just run the clone command on GitHub. So I'm not going to run it because I already have a clone. So it's in the repo, you run git clone, and once you run it, it creates this folder. and you just navigate into that folder. Once you're in the folder, there's a setup script. So we can run it. I think I've already ran it before, but just run it again. It basically checks a bunch of things that are and aren't installed. So if UV isn't installed, it'll install it for you. If GitHub is not up to date, because we're using DataLad and it's very sensitive about versions, it'll install a version that is compatible. JQ is just this parsing, bash parsing package that installs, and then we confirm the Git Annex version. The sync is then performed for the UV setup. So we have a PyProject YAML file, which has a bunch of our Python packages that we're using. So I just install those, which includes obviously PyBids and Fitlins, etc. Once it finishes, it installs also a kernel for your notebooks, because I like to check things in a notebook before I run them for my models, because it takes, I don't know, maybe 2 minutes, 1.5 minutes to run in a notebook to double check what my model design matrix looks like, rather than starting it, waiting some minutes, it failing, and then we have it go back. Okay, so in this case, we have our stuff set up, and oftentimes you will always already have things basically loaded once you run the setup, but you have this folder for that is created for the virtual environment from UV, which when you start and you log in, you just need to source and activate it. So there's this script that you just run, and it basically activates the environment, and we're in this kind of path where we can run these things. For the first time, you want to modify the paths file. So there's a data set folder, which I may refactor how it's structured. I might, anyhow, I won't belabor it, but data set folder. So basically where the input, fMRI prep, and analysis outputs go, you want to update those to yours. Where the repo is located. So the folder, the scratch or temp folder of fMRI prep singularity image. And so you just use a singularity build command, which I provide on the repo for a version, and you update the version here. That is then used in regenerating those fMRI prep. And because we will be using fMRI prep, I don't think a free surfer license is required, but I still include it just in case, because sometimes things change with how fMRI prep may run. So it may need a free surfer for a step. So once you update these 4 steps, you're basically ready to go into the scripts folder. And then you start with the first step of effectively saying, we want to download this first data set. And when it starts running, and for the record, I already ran the longer part, which is the fMRI prep derivatives. So it'll, like I said, it give you this report of checking the files for this data set. And you can see the inputs and number of files are way smaller than the fMRI prep. And so once we're ready, we just hit yes. If we're not, we hit no. This is just cloning the bits input, because we don't need all of it, because it's the full derivatives. And there's a step where it creates symbolic links, given how I have the folder structure. So it basically makes hard links of the fMRI prep derivative in a fMRI prep derivatives folder that it then kind of uses. And then this one takes a few seconds to run. Because it's having to create a symbolic link for everything that's in there. But once it's run, it starts to basically give you some spit out of this report, which is the final step. And so that report spits out to the console, which I'm currently refactoring. So it spits out, for example, here for this data set, fMRI prep, bids inputs, the task. If you're running minimal, this will oftentimes give you nothing, because there's no, it doesn't recognize some of those things as it, so because it's not finalized. Bold volumes, number of files. For each task, it'll give you this output to the screen. And then, as I mentioned, if they don't exist, it'll create these subject, contrast, JSON files, and then the README file, and then the basic details file. Once it's finalized, this error I fixed. It's just not in this version, so you won't see it when you do it. But once this is finalized, you basically can run the so So if you're in stats models and you go to, I think there, where this folder. So you open up this file and then you specify what you want done to the dummy volumes and their preproc. So if they're dummy volumes, change it to an integer. If you want value pre-processed, you change that to a true. And so that's already done. And if we're modifying for this data set, we open up this modify events file. And like I mentioned, there's already a lot of things that are already in here. And so you basically just add, there we go. So you just basically add your own function for what you're modifying. And once you've set that up, maybe you have a data set which is compatible, which has the onsets, it has the durations, it has the trial types, and they're all structured in the way you need it. You don't need to add that at all. And so you can just transition straight into running it. Basically, what it'll do is, let's see, where's our data folder? So our data folder is here. So it's basically going to search for anything that has any of these files, and it will follow the recipe of modifying based on some condition for trial types and values that exist there. The biggest culprit of errors sometimes is, say, a trial type has NAs that you can't parse an NA into a call name, which would be a problem. So it iterates, finds those, and just updates them according to your formula. After which you create your batch spec file. In my case, it already exists, so running this won't really create anything. But like I mentioned before, it basically just, it will ingest this contrast file and this subjects file, and then it'll output this specs JSON file, which will give it the recipe. And in this case, the spec JSON file is just, whoops, not this. It basically gives it all the subjects, it gives it the task. There's not a list of sessions because when OpenNeuro dataset doesn't specify a session label, it's an empty field, so there's no sessions. And then it has your run level, which we're basically saying run this for each run and subject, has transformations that are basically creating the trial type names, kind of renaming them, creating another regressor for RT. We're factoring this trial type value and this value to so we can have it available in the format that's necessary to then we convolve and then build our model, so on and so forth. And kind of like how I mentioned before, contrast weights, etc. So that's gets all populated. In your case, when you do it, a lot of these things will just, if you update it, they'll be the updated versions, but the models will be some boilerplate that you will want to update yourself. Once that runs, you basically have the option of running the fourth run fitlist command, which again takes the data set and you have the task name, or alternatively, you effectively will run the SBatch script. So you are going to submit the cluster, run the Fitlins, and it's just the same thing, just in a different folder. And like I mentioned before, you will update the SBatch with the partition name, and then you will add an account name below because that's what you need, and update the email address. But everything else, as I mentioned before, is in here. Here, when you the environment, which you control the smoothing type, so you can modify what level smoothing is made. which I'm going to update to make that more of a dynamic option that you can use. And it basically runs the UV command submission of Fitlins, which specifies the bids, the output, participant, the model, fMRI prep directory. I always ignore these physio, JSON, TSV, GZ files because they exist and Fitlins will find them, but then have a problem with them because it's not using them correctly. Um, and if subjects have things missing, it drops it. This currently has this thing where even though everything runs, the HTML report that Fitlins generates just says a lot of things are dropped, which is wrong. And so Chris is going to be refactoring and clean that up. You specify the
I have
space.
a question about the drop missing. Is that if the file is missing or if trials within the file is missing?
So, so the drop missing is a subject. If you cannot compute a contrast for a subject, it won't run it. Or if you don't have
Okay.
runs for a subject, it'll drop the subject.
Okay.
So basically, it's a very uh, like uh, kind of like when yeah, it's not an elegant solution, but it at least better than it failing.
Yeah.
But where I'm adding some things for quality control to visualize what counts there are. So you have an idea like, hey, everyone has this. And each step of these, when you run them, it does spit out a report of like, hey, this subject has only one run, but you're expecting some people have two. So try to iterate at each step so you're aware of what are missing. So you don't add
Yeah.
subjects that don't have trial types. But yeah, this is just like it drops subjects if they're missing or runs if they're missing. Good question. Thanks for that. And this, you just provide the space, the MNI space that you're running on, the label for those derivatives. Again, the smoothing goes here. We're using the estimator here, which is Nylearn, but you can update it to AFNI. Eventually, we'll have hopefully an FSL option. And the rest is just the memory we're using, the usage, which is if you don't update the usage at the top, you don't have to update it below. So that's basically it. When you run it, it'll won't show up here because I don't have any outputs for it ran, but it effectively runs Fitlins, spits out the analyses in the output file folder. It will create a log folder in this cluster jobs where you can check if it has errors. And then once you're done and it's successful, that's when you run the report for a given subject. So again, ID, it'll effectively run, check a bunch of information, grab some files, and I'll show you the report what it creates, rather than going over here because it's not visually appealing here anyways. So that's the whole process of running this workflow. It's 5 scripts, and the most involved are the modifying the events files and your spec file. The rest, it just kind of does dynamically. And except the example, well, I guess I'm lying now because I just showed you an example where it didn't run. So it's not dynamic if it's failing, right? So bite my tongue on that. But I'll now kind of show you an example of what these reports look like when you actually finish running them. But ask questions because I know we have 7 minutes. Let me just share this screen. So that way you're familiar with what the reports look like. So again, all these things are on the repo. And as I mentioned, all the tasks that are completed are here. But just going in the stats model specs, we'll go for this subject. And so when you run, download, it creates this output. Right now, we just refactored something yesterday to add below each task how many subjects, how many runs per subject, and what are the list counts of run types. So some people will have 1, 2, 3, others will have 1, 2, 3, 4, 5. Then it gives you a count proportion of distribution of how many counts for each list type there are. So you easily see like, hey, not everyone has 5 runs. These subjects don't. What am I going to do with that type of deal? As I mentioned, MRTC has this link where it just give you the distributions of these values. And this is an HTML preview option, which someone created, which is neat. And then just the group report is what we'll review. So this is, when you run that, this just gets created automatically. You don't have to do anything. So specify data set, the size of the Fitlins directory, the folders, any papers that are specified in the basic details file. So this starts empty, but you can create a list of citation links that'll populate. It'll basically list those papers here, and then it gives you the boilerplate. So for first level analysis, we had 16 subjects, whole brain mass univariate, 9 regressive of interest out of 10 total regressors, convolved with so-and-so. Where 4 were parametrically modulated. We have a design matrix, which included convolved and non-convolved, and nuisance regressors. It kind of covers the motion regressors. It covers the model implementation. So, we're using this as AR1 model. We're using the Nylearn estimator. We're using a specific smoothing, and how each thing is being regressed. It's give you information about outputs that Fitlins provides. The subject group of, I don't know why I'm keep clicking on those links. So subject little models here, if there's multiple runs, it doesn't use precision weighted. So in Nylearn, if you're familiar, this would be false. So it's just taking the average, right, rather than some weighted average based on those variance components. And then specifies the group models. And so in section 2, you have more analytic data details. Was this ran, this one, as your regressive of interest. Intercept, I label as interest by default, even though people say, well, intercept is not of interest. But if you're using an implicit baseline, it is of interest because that is what you're basically compared to. Then you have the convolved regressors. This is made by case conditions, so they won't always identify correctly. I'm thinking about ways of maybe using an LLM to make it more accurate, but so far it's working 10 at 11 times. I'll bite my tongue again, so I don't see purpose of spending like 2 cents to do that. Creates the nuisance regressors, gives you all the contrasts of interest, specifies their weights, so no one has to guess what they're there. Creates the model figure regressor, just grabs the first one as an example, which is also stored in the subfiles directory for your reference. It gives you contrast weights and more of a visual, which Fitlins generates. Computes variance inflation factors, so for your contrast and your regressors. So if you are familiar with Jeanette Mumford's work, she has documented why you should also pay attention to contrast variance inflation factors. Gives you a voxel-wise variance explained map. So oftentimes we do a bad job QCing, and if free surfer fails, you'll usually see this come out in bold maps. And when you take averages, I found with variance explained maps, you'll have like these halos because some subjects are bad. And then it uses an estimation of dissimilarity coefficients as well as proportion of voxels outside of the MNI mass to basically generate a thresholded outliers to check for. So basically say subjects here that should be looked at, and it tells you how they're cited. And then finally, it gives you a Z cutoff of 2-3 uncorrected statistical maps for all the contrasts that you ran. If you have multiple sessions, I'll do it by session. So that's basically the workflow in a nutshell and the report as it's laid out here. But in the last few minutes, if anyone has questions or recommendations, especially, I love any input of like, hey, I don't like this. Can you do this way? That's very helpful.
I can just do a quick one. So you said that the maps that are output are uncorrected. Is there a way to do like cluster correction on that? Or like how would you do that next step?
Yeah, so I'm trying to motivate Chris to include cluster corrections and use them, because right now they don't give that as an option, but that's a simple modification of the workflow, and I think it's an essential one. And while like Nylearns and other algorithms, their cluster correction algorithms are slow, it should be an option because that's how people report. So like, why we can't just threshold stuff. But so one thing is, because the run level and subject level exist, one could easily rerun the group map externally on their own and cluster correct it. I don't like that because that's the not definition of reproducible and automated. So I'm hoping in the next, because Chris has been gone on vacation a month, so we're going back and talking fixes next week. So that is one of the things that we'll bring up.
All right. Well, Michael, thank you again for your time. This is really interesting. I'm looking forward to trying this out. I think this is a need, especially with these larger data sets. So this is great.
Yeah, thanks for listening and joining at 10 a.m. on a Friday.
Yeah. Well, it's a little bit later than we usually meet, but yeah, we appreciate this very much. I know we're at time. I know people have to go, but thanks again, and I'll see all of you next month. We're at the same schedule, but we'll switch it back to 9 a.m.
I
All right, everyone. Have a good weekend.